Okay, we will move straight into our first presentation of the day. So first up, we have Renda Yiğit and CAMAL GENÇTÜRK of Turkish Aerospace presenting on patch management of satellite flight software. And so you're welcome to start sharing your screen.
Hello, everyone. Thank you, Brandon. Hold on a second. So can you see my screen?
We can.
All right. Okay, so my name is Renda Yiğit. I'm here with my friends CAMAL GENÇTÜRK, Ezgi Kutlumurat, and Feyzanur Özcan. We all work in Turkish Aerospace, which is a company that specializes in aerial vehicles like airplanes, drones, helicopters, spacecrafts, all that sort. And we work in the software department of the space division. And we have recently implemented the patching mechanism for our flight software, and that is what we are going to be presenting today. Okay, so this is the outline of our presentation. We will first start by explaining why we need to be able to update our software, why it is important. And then we will go on into checking out the ECSS standards and what they mention about patching. And then we will show you two different patching techniques that we have tried out. And then we will show you two different approaches to apply these patches that we have generated. Okay, so why do we need to be able to update our software? We need to update our software to fix errors, to improve certain capabilities of our code, and to basically maintain it. And this process has to be done very fast because your mission can be very important. System availability of your satellite can be very important. Also, in some satellites, like the one you can see in this animation, low Earth orbit satellites, they regularly enter and exit the communication cone where communication is only possible. So your patching process has to be done as fast as possible. Your updating process has to be done as fast as possible. And on the right, you can see an example image can be 1.37 megabytes. And to upload this image, we need something around 6,000 telecommands to transmit. And a satellite would execute all of these commands in more than 10 minutes. So like I said, it's very important for your updating process to be fast. That is why it makes more sense to patch your software rather than do a full system update. And when we say patching, we mean only modifying the parts of your software that is supposed to be modified and leaving the rest alone. All right, so the ECSS standards do not mention any standard approach. They only indicate that there are three criteria that we should be considering when applying such mechanisms. And the first one is we need to take into account the availability of our system. Like I said before, your mission can be critical and you should not interrupt it. And the second criteria is bandwidth, TMTC bandwidth. And the more bandwidth you have means the faster transmission that you will have. So this also helps us with speed. And our third criteria is available memory size. You cannot transmit an infinite amount of data to your satellite. You have a limited amount of memory, and you need to consider that while you are patching your system. And all of these are very important for the long-term maintenance of your flight software, and you can see this at the bottom right over here. ECSS standards emphasize on this very much. Okay, so these standards show us three different cases Okay, this is the first case. Here we can see this pink area over here indicates our memory, our entire memory. And this blue area over here shows us the flight software, okay? This is our flight software. And in case one, you do not patch your system, you do a full system update. So we will be modifying all of this area. All right. And to be able to better compare these cases, I'd like to show you this diagram. So let's assume that our entire image can have certain procedures like procedure A, B, and C as shown over here. Okay, now let's check out case 2. In case 2, we will be trying to only update a part of our flight software, like you can see in this blue area. And to show a diagram for this, we can say that if we modify something at the center of our image, say procedure B, if we modify it, it can expand, and we can have a picture like this. Okay, and case 3 is where we have a dedicated area in our memory where patching will be stored, as you can see here at the bottom of our image. And also we will be modifying parts of our code that have function calls to the patches that we have all the way down here. And to better understand this, we can show this diagram. This is our old procedure B. We will be only modifying its first line and not touching the rest at all. And the modified the new procedure B will be all the way at the bottom over here. So this line will be a jump instruction, and we will be jumping all the way down to our new procedure like this. Now I will explain this better in the next slides. Okay, so in case 2, we added a dummy function, an empty function, as you can see over here, to our image. And then we compared our original image with our updated image. And on the left over here, inside this purple box, you can see all these red lines. These red lines indicate the difference, all of the difference between these images. Well, why is it this much? Why is this difference so much? That's because you can see that we added something to the middle of our code. Our procedure B expanded, and that's why everything beneath it have shifted down. And that has caused a tremendous amount of change between our images. Also, translating all of these changes to telecommands, you can see that you have to transmit more than 3,000 telecommands to your satellite if you were to use this case. And to execute all of these telecommands, your spacecraft would waste 5 minutes, more than 5 minutes of time. This is not efficient at all. So let's check out case 3. And in case 3, you can see that we have very few changes over here for the same function. And our telecommand count has gone down all the way to 2. And executing all of these would be only 2 milliseconds. So let's see what we did here. You can see that we added 2 files, patch C, patch H. Here you can see that we tell our system that these new functions are going to be added into a new section in our image called patch text section. And also we should use the weak symbol of GCC to tell it to ignore our old function. So you can see that we are not modifying our old procedure, and we are adding our new procedure into a new area. Therefore, nothing is shifted around, and we have minimal change. And that's it for case 3. Oh yes, now to better understand what we did here, we must understand how an ELF structure works. Because we store our flight software image inside an ELF file, which stands for executable linkable format. And from this image on the left, you can see that ELF files have certain sections in them. And for us, these two sections, called the text section and data section, are the most important sections, because they store code and instructions and variables. And these are the parts of the ELF file that we normally modify. And like I said, we need to add a patch section to our ELF structure, like you can see over here, this orange area. And we achieved this by modifying our linker file, which you can see a part of over here. Yeah, that's how we achieve this. And yeah, that's how we achieve this. So let's compare all 3 of these cases. Again, we can see that in case 1, where we do not patch our system, where we do a complete update, we would need more than 6,000 telecommands, and executing all these telecommands would take more than 10 minutes. In case 2, we would use a little more than 3,000 telecommands, and the time to execute these would be a little more than 5 minutes. And in case 3, which is the most efficient one, we would need only 2 telecommands to transmit, and executing these on the spacecraft would take only 200 milliseconds. So like I said, case 3 is the most efficient one. This is the one you will be mostly using. But there might be cases where your patch data might be too large to fit inside this patch area. And in those cases, you might consider using case 1 and doing a full system update. All right, now that we have generated our patch data, now we need a way to apply them on our spacecraft. And for this, we have 2 different approaches. In the first approach, we use our bootloader. And here you can see that when using this approach, you can store multiple patches in your satellite. And to manage these, we have a patch configuration address. So when our bootloader starts, it reads this address and determines which patch to apply. And in the flight software approach, we do our patching process in runtime rather than boot time. So that's the main difference between these 2 guys. So let's better analyze them in the next slide over here. So let's say that we want to use the bootloader approach to update our software. So we would start by creating a new image, as you can see here. And then we would provide this image and the currently installed image on the satellite to a tool that we created called the patch data generation tool. This tool will basically compare these 2 images, and it will generate the required telecommands. And we will grab these telecommands and transmit them to our satellite. The satellite will execute these telecommands and copy the data to the bootloader patch area. After this, a simple restart will have us go into the flowchart that we showed you in the previous slide. Our bootloader will start and it will read the patch configuration address we have set earlier, and this will show the bootloader that there is a patch to be applied, and this will apply the patch. All right, so in the flight software approach, we do the same thing. We create our new image, we provide this image and the original image to our patch data generation tool. It creates the required telecommands. We then transmit these telecommands to our spacecraft, but as we transmit these telecommands, This time, the spacecraft has the flight software image loaded onto its RAM. And as it receives our telecommands, it overrides the areas in the RAM with our telecommands. These telecommands basically have information in them that indicate where in the memory they are supposed to overwrite. And after all of these telecommands are sent, the image in the in the RAM is fully patched. And after this, the flight software does a simple check on this image inside the RAM. If all of these checks pass, it will copy this image in its RAM to its ROM memory. And this change is permanent. You will lose your original image. And after this, doing a simple restart will have your computer boot into your new updated image. So in this chart over here, we can see a comparison of our approaches, and I need to mention that we ignored the TC execution times and CRC checks. So we can see that the flight software approach is a straight line. As your patch size increases, the time for your patch does not change, because the timings you see here are the timings for copying your image, your updated image from your RAM memory to your ROM memory. So no matter how large your patch is, your image will be the same size, and therefore the time to copy this image will always be the same. But for the bootloader approach, the patch size does affect your speed, because the difference here is when you boot, your image is copied from your ROM memory to your RAM memory. And after this copying process, the selected patch is also copied onto the RAM. So the larger patch you have will have a longer time to copy. And that's why you can see this line over here gradually increasing as your patch size increases. All right, so to sum up, we can compare these two approaches, saying that in the bootloader approach, the patching process is done at boot time. And in the flight software approach, the patching process is done at runtime. And in the bootloader approach, you do not lose your original image. This might be important for you. You might need to have the ability to go back to your original image in case you made any mistakes or something. But in the flight software approach, you do lose your original image. Also, with the bootloader approach, you can store multiple patches on your satellite. And in the flight software approach, you do not have this function. You can only store one patched image. But we can say that this is easier maintenance because you do not have to keep track of all those patch configurations in your memory. So yeah, that's all. You can see our references here. Thank you for listening. If we have time, my colleague CAMAL GENÇTÜRK and I can answer your questions.
Thank you so much, Renda. Yes, we do have a few minutes for some questions, and so I'll start going down the list for what we've got. First question from Clyde. How do you protect the integrity of the patch when uplinking?
Jamal, would you like to answer this one?
Hello, everyone. I hope you can hear me well. For the integrity checks, we are using CRC checks for every telecommands to see that if there is any issue with our data that we get from telecommands. And also we are using CRC checks for our patched image to see that if there is any error or failures in our image. So I can say that we are using CRC checks for telecommands, for every telecommands, and also the patched image.
Okay. Next question from Ingolf Steinbach. How do you deal with modifications which would pull in new code from libraries which are not directly under your control, for example, libgcc? That new code would end up in the normal .text section and would potentially cause a shift in parts of unmodified software.
Jamal?
I think for this case, we need to see that if this new codes just exceeds the area that we are using for a patch section, maybe in this case, we need to update our entire image. And then we will have a new image, new original image, which has a new text section, data section, and also the patch area that we are using. And in that way, we can just get rid of this issue, get rid of this error, maybe.
Okay. Next question. Do you use any recovery mechanisms?
Recovery, yeah, like in the flight, in the bootloader approach, we can go back to our original image. If I understood correctly. Jamal, if you have anything to add.
Yes. Actually, our recovery mechanism is the approach that we are using, bootloader approach, and we have the opportunity to go back to the original image. And in that way, actually, in some missions, you need to, or especially if you see an error with your patched image, you need to go back to your original image. So we can say that this is our recovery mechanism for this case.
Okay. Question from Joel Sherrill. Did you consider using dynamic loading, such as supported by RTEMS and VxWorks? Did you even have that available as a design option?
Actually, we didn't use this opportunity for us, but maybe we can take a look at it and see if it's go well with our design, and that, in that case, maybe we can use that option. Thank you.
Okay. Next question from Leonidas Kosmidas. What happens when you use the flight software approach, but there are still some functions already called in the stack? Are you walking and patching the return addresses in the stack?
You mean while it's still running? I don't think I understand this question. Jamal, would you like to answer?
Actually, I also didn't get the question clearly. Maybe we can have a better understanding for this question. Or maybe we can answer this question by using Slack in details. I don't know.
Okay, we can move it over there afterwards. Next question, is the patch in RAM or flash?
When using the flight software approach, you do your patching in the RAM first, and then you overwrite the image in your ROM memory after you have patched the one in your RAM. And in the bootloader approach, you do not modify your image that is in the ROM memory. You basically transmit, your patches to your RAM, and then those will be copied to your to this area that I mentioned over here. If you have anything, Jamal.
Yes, I think also we got this question in the first 2 or 3 pages of the slide. I think the question was about maybe we can show the linker and see that we loading this patch area to the RAM area while running the image. Maybe this can be also another answer for this question.
Okay. Next question from Thomas. The right side of the plot for times seem to show the patch times growing as size increases for BL method while flight software method stayed the same. If you extend the graph to the right, do they end up taking the same amount of time?
We did not test that, but Jamal, if you want to add something.
Yeah.
But before that, I mean, I don't think they are going to ever intersect with each other, because that would mean your patch size would be, too large.
Yes, that's true. Actually, for this example, we used 10 kilobytes of patches, and in that case, we didn't see that they are crossing each other. But if you have too large a patch area, maybe you can have it, but it can be unreasonable to have such a big patch area, because in that cases, maybe you can consider that you updating to your entire image.
Okay, and time for one more question. How do you locate the position in the onboard binary file to put the patch?
How does our tool work? This tool. Jamal, do you want to answer this one?
Yes, maybe we can answer it. We mainly locate our patch area to the bottom of the image to not to have a big changes or big size of differences in our images, because if we have too much changes or too much differences in our cases, so using a patch can be unreasonable for us, because to make the differences slower or lower in size, we need to locate this patch area to the bottom of the images.
Okay. We do have a couple of questions left, but no more time, so I think we'll move some of those over to Slack if you'll join us over there. Jamal and Renda, thank you so much.
Thank you very much.
Thank you for having us.
Yes,
Absolutely.
thank you for having us.